Welcome to Unit 6, where we're going to talk about congruency, and specifically how to prove that triangles are congruent. Remember that our vocabulary is always circled and our theorems are boxed. Our first vocabulary for this unit is congruent figures, and those are figures that have the same size and the same shape. You can see on your handout an examples of congruent figures, even though they may not be oriented the exact same way, they are congruent, and also examples of non-congruent figures, triangles that have a different shape, different angle measures, or are different sizes. Their corresponding parts, which means that they're matching sides and angles, are also congruent. So matching sides have the same length. Matching angles have the same degree measure. Those are for corresponding parts. To name congruent figures, you need to list the corresponding vertices in the same order. Remember, vertices, those are going to be the vertexes, the angles. And you list those in the same order. So if A is congruent to B, they need to come in the same order. We'll see examples of that. Another term we have is rigid motion, and our goal is to understand congruency in terms of rigid motion. Rigid motion is taking an object and moving it to a different location without altering its shape or size. So two objects are congruent if you can go through a series of rigid motions to get them on top of each other. For example, reflection is a type of rigid motion. I can take this smiley face and flip it over like this, and it will be on top of this one. Rotation is another example. I can take this heart, turn it 90 degrees clockwise, and it will go right on top of this one. Transformation. I'm sorry, that's supposed to say translation. Translation is another example because I can take this D and slide it, and it will end up being right on top of this one. So our examples are reflection, rotation, and translation. Those are all examples of rigid motion. Let's look at a few examples. So in example 1, we are asked to identify the corresponding parts of the congruent parts of congruent figures if Hij is congruent to LMNO. So these are quadrilaterals, and we know that because they have four vertices. So I've drawn a picture here, and you have one on your handout, but I don't even need the picture in order to complete this problem. So I know that when I name congruent figures, I list their vertices in order. So I know that H has to be congruent to L. Those angles must be congruent. And you can see in my angles that I know that's so. And you can even see in the figures that that is how they line up. In fact, in order to put this figure on top of this one, I would need to go through a series of rigid motions. I would have to slide it over this way. Perhaps I'd have to flip it, maybe even rotate it. So let's get back to how we identify congruent parts of congruent figures. So looking at the names, if I look at the side between HI, I know that that is going to correspond in this quadrilateral to those same two letters, the first letter and the second letter. So HI is congruent to LM, and I have that written here. If I look at the second and third letters, I can do the same thing. IJ is congruent to MN, and I have that here. Let's look at the last two letters. JK is congruent to NO. And again, if you look at the image, you can confirm that all of these are correct. Same with just the angles. And the last side, of course, is also congruent, the first letter and the last letter. When we look at the angles, we can see that all I'm doing is matching up the letters in order. H and L, I and M, J and N, K and O. Very simple to understand. Once you understand they're labeled, the vertices are corresponding in order of naming them, very easy to understand which sides are congruent and which angles are congruent. Here's another example. Are the triangles congruent? So you have on your handout this same diagram where through a series of reading what the diagram is telling us, I can write the statements. And on your handout, you are going to complete the reasons in your notes. So I have that angle A is congruent to angle E, and that angle B is congruent to angle D. And I know this because that's given based on the arcs inside. So B and D both have 2 arcs, and A and E both have 1. So again, the reason for that is given based on the arcs. Statement 2, BCA is congruent to DCA. These 2 angles are congruent, and that's because they're vertical angles. Third statement, AB is congruent to ED, and again, that's given based on the markings, on the tick mark. Fourth statement, BC is congruent to DC, and that's given because they're both labeled with a length of 4. CA, my fifth statement, is congruent to CE. Again, that's given because they're both labeled with a length of 6. I have confirmed that the 3 sides are congruent and that those 3 angles are congruent. Triangles only have 3 sides and angles, so we're in business. I can now conclude that triangle ABC is congruent to triangle EDC because all 3 sides and all 3 angles are congruent. And again, look at how I label these. I know A is congruent to E, so they both need to be first. Those could have been last, but they had to be in the same position in the naming. B and D, both in the middle. I couldn't have CED here. That wouldn't work. It wouldn't be congruent because my corresponding vertices are in the same place. Here's a third example, an algebraic example. This is how we can use congruent figures. So, if I have 2 quadrilaterals, ABCD and QRST, how can I figure some things out about angles or sides? I know that the measure of angle A is x minus 10. The measure of angle Q is 2x minus 30. They're asking me what is the measure of angle 10. I can look at the way that these quadrilaterals are labeled, and I see that A and Q are both labeled first. Therefore, I know that they are corresponding parts of these quadrilaterals. And if they're corresponding parts and they're congruent quadrilaterals, they must be congruent. So I know that angle A is congruent to angle Q. And from the definition of congruency, I know that the measure of angle A is equal to the measure of angle Q. Now I've just substituted in the algebraic expressions for the measure of angle A and the measure of angle Q, and I solve for x. I found x to be 20. But they didn't ask me for x, they asked me for the measure of angle A. So I need to go back. And when I go back, I put in the measure of angle A back to its expression, and now I can substitute in my value of x. I found x to be 20, so I substitute in 20. I find the measure of angle A is 10 degrees. I also, therefore, know that the measure of angle Q is 10 degrees because I know that those angles are congruent. Now let's look at this very interesting theorem. It's called the Third Angle Theorem. And what it tells me is that if 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles are congruent. So this seems clear. Let's go over this. We have 2 triangles, and I know that angle A is congruent to angle D. You can see that by the markings. Angle B is congruent to angle E. Again, you can see that by the markings. And the conclusion is that angle C is congruent to angle F. Of course, we can prove this by the triangle sum theorem. Right? The total needs to add up to 180. So if you know that these 2 are the same and these 2 are the same, then there's only one number left that can fit for C and F that will add up to 180 with those other 2 angles. This theorem is incredibly useful when you're trying to prove that triangles are congruent or different parts of triangles are congruent. Here's an example. In triangle MAP and triangle TIE, angle A is congruent to angle I, and angle P is congruent to angle E. So you can see that the second letters are congruent and P and E are congruent. Now, what is the relationship between angle M and angle T? So, we know that by the third angle theorem, if two of those angles are congruent, A and I are congruent and P and E are congruent, so if two angles of one triangle are congruent to two angles of another triangle, then those third angles must be congruent. So that means that angle M must be congruent to angle T. Angle M must be congruent to angle T, again, by the third angle theorem. Now let's solve a problem using it. The measure of angle A is 52 degrees. The measure of angle P is 36 degrees. So I know what A is, I know what P is. Now I need to find T. T is all the way on this triangle. But I could solve this two ways. I've chosen to solve this knowing that angle M must be congruent to angle T. I've written that here. I've proved that up here. I could have also said that angle A is congruent to I and angle P is congruent to E, and then solved angle T that way. Let's stick with this direction. So if M and T, if these two angles are congruent, and I know that by the triangle sum theorem that the measure of angle M plus 52 plus 36, the other two angles in that triangle, they must add up to 180 degrees. From there, I used algebra to find the measure of angle M is 92 degrees. But again, since the measure of angle 2 is equal to the measure of angle T, that's also the measure of angle T. Angle T is 92 degrees.